In this video, we are going to go over the question number 3 and 4 in the friction and forces packet. And we're going to start with question number 3, which has a mass of a block of 0.5 kilograms on top of a slab that has a mass of 3 kilograms. And initially the slab's at rest and the block is moving with a speed of 4 meters per second to the right. There's a coefficient of friction between the block and the slab of 2 or 0.2, and there's no friction between the slab and the horizontal surface. As this object moves across, as the block moves across the slab, the friction between the two causes a force to develop both on the block and on the slab, and this moves the whole system forward. Note that because the block is moving initially, the whole system has momentum. We're not going to solve this through momentum, but you could solve this through momentum. And that's why the system moves. Initially, what we're looking at is this scenario. We have mass of the block multiplied by acceleration due to gravity, which is acting downwards. That is counteracted by a normal force, and we have an unbalanced force of friction acting on the block. Something very similar happens with the slab, except it has to support both the mass of the block and the mass of the slab because the block is resting on it. It has a normal force and the same exact frictional force acting on it. So this force of friction acting both on the block to the left and on the slab to the right is what is acting on both systems. So we have a net force on the block, which is equal to the force of friction, and we have a net force on the slab, which is equal to the force of friction. So we're going to find the force of friction. The force of friction is equal to the coefficient of friction multiplied by the normal force, and the normal force is equivalent for the block of mass times mass times gravity, so this is 0.2 times 0.5 kilograms times 9.8, and that is equal to 0.98 newtons. And I left off the 9.8 meters per second squared on the end, but this should be 0.2 times 0.5 kilograms times 9.8 meters per second squared. That is equal to 0.98 newtons. From here, we take two steps. The first step is we find the acceleration of the slab, which is that force of friction at 0.98 newtons divided by the mass of the slab, which is 0.5. And we do something very similar for the acceleration of the block. That is the force of friction, the 0.98 newtons, divided by the mass of the block. That is the 3 kilogram mass. Note that the block or the slab underneath does not accelerate based on the combined masses. It only accelerates based on the net force acting on it. Because for the combined masses together, the net force is 0 because the force of friction from each of the scenarios cancels each other out. So the acceleration of the slab only depends on the mass of the slab. The acceleration of the block only depends on the mass of the block. Once we've found these two accelerations, we can start taking a look at the fact that because the two velocities always end up in the same spot, so the velocity of the block and the velocity of the slab ultimately obtain the same value, we can write equations relating the velocities, the final velocities of both the block and the slab relative to their accelerations, their initial conditions, and time. Setting these two equal to each other, we come to the bottom down here, the very important equation that says the velocity of the block initially, which is 4 meters per second, plus the acceleration of the block, which we found, multiplied by time, equals the velocity of the slab initially, which is 0, plus the acceleration of the slab times time, and we found the acceleration of the slab. So in this scenario, the only thing we don't have is time. And we can solve for time. Having that time, we can find the final velocity, and I'm going to use the slab here. So we say that the velocity of the slab final velocity which is equal to the final velocity of the whole system, is equal to its initial velocity multiplied by the acceleration of the slab, which we already found, times the time, which we already found. So it's velocity of slab equals VO plus acceleration times time. Once you have the final velocity, I left off how to find the displacement. You have plenty of kinematic values to follow that and just determine the displacement. Using the slab is what I did. Question number 4. In this question, we have a car with a mass m, initially at rest. It's driven to the right and along a straight horizontal road. The engine is causing it to have an applied force of F sub 0. But as it picks up speed, it starts to encounter a resistive force that's equal to negative kV, where K is the velocity, or K is a positive constant, and V is the velocity of the car. So part A asks us to draw a free body diagram of this. And we can see that we have the applied force, F sub 0. It's opposed by the resistive force, kV. We have mass times gravity pointing downwards, and we have the normal force pointing upwards. From this, we can see, since the mass times gravity is going to cancel out the normal force, the net force that we see here is going to be the applied force F sub 0 minus kV. That is our applied force. And we subtract the kV because it's pointing in the opposite direction of F sub 0. The next question asks us to find the acceleration of the car. We just talked about the net force being F sub 0 minus kV. We know the mass of the car, so we can determine the horizontal acceleration of the car. And this is really our starting point. Just note that the F here, I'm referring to the net force of the car. The next one is a bit of a difficult question. It asks us to find the velocity of the car. Now, for C, which this is the question we are on, the initial velocity, or the velocity here, you need to take the derivative, or you need to take the integral of the acceleration function we found in the previous question. Now, this gives us a term in the denominator. Ultimately, it goes to a natural log. Once we take the derivative of that, or once we take the integral, we get a natural log. Solving for both sides, we need to have this set of terms. So we'll talk about this a little bit in class. I'll show you the individual steps. But I want to give you the answer so you can kind of take it from there. If you are going to try this one, you have to replace your acceleration with dv dt, split your variables between sides, then take the integral of each side, go through the natural log. Please note that there is going to be one chain rule that's going to be acting here when you go through this equation. Moving on to D, the velocity is a function of time graph. I've just identified the initial and eventual values here because we want to know where we start, we want to know where we finish, and I'll leave the shape of the graph between those two positions to be up to you, but the question does ask us to label the important values on the vertical axis, and so these are the two important values. At 0 meters per second, that's where we start. Eventually, when our velocity is equal to our initial force divided by k, that's going to give us a 0 slope in this graph, and then our graph will straighten out. For the acceleration as a function of time graph, initially FV is 0, so that means our value for our initial acceleration is going to be F sub 0 divided by m meters per second squared. So that's acceleration equals force divided by mass. But as this FV contributes increasingly to our problem, we're going to find that we're going to be trending to a scenario where we go to 0. So this is our initial and our final conditions for the acceleration as a function of time graph. And once again, for both these graphs, I'll let you draw the shape between the two. Try to keep your wits about you in the sense that what would make sense realistically for how these graphs should look. That'll be it for these couple of questions. I will cover especially the last question, number C, on Monday in a little bit more depth.